Hello and welcome to our tutorial on permissioned blockchains. We're going to cover various aspects of blockchains, properties, techniques, and applications. This is, I want to emphasize, on permissioned blockchains and not permissionless blockchains. I will explain briefly at the very beginning the difference, but just so that you know from now. This is a tutorial that will be presented by Mohammed Amiri, who was a student of Divi Agrawal and myself. All of us are presenting. We come from UC Santa Barbara. Mohammed was a student at UCSB and now is graduated and is a postdoc at University of Pennsylvania. So you've all heard about blockchains. And the most common context for people talking about blockchains is in the context of cryptocurrencies. So what's the idea of these cryptocurrencies? Well, if you think of how we normally interact with each other financially, there is a bank, as you see here, which is an entity that we all trust. We put our money in the bank, and then if I want to give Divi a certain amount of money, I write him a check and he goes to his bank, I go to my bank, and the two banks transact with each other, and the transaction is performed where the money that the $50 that I want to give to Divi are transferred from my account to his account. That's a traditional way of looking at transactions and banks. What cryptocurrencies do, and this idea was basically developed and innovated initially in Bitcoin, is that you replace this trusted bank entity with a peer-to-peer distributed system where everybody keeps track of everything that is happening. So instead of having one bank that has all the information, you replicate all the transactions that are occurring on various different entities, and each of them keeps track of everything that is happening. So in a way, you have complete replication of the entire history of all the transactions that have been occurring in the system. So a blockchain is basically a ledger or a log of all the operations that have happened, and it is replicated for fault tolerance and for performance reasons. And in general, in a cryptocurrency system, you'll have all these different entities that are called miners, and they keep trying to solve a problem. And once they solve it, if they succeed, they become the winners. They can add the next block to the blockchain, and they distribute it among everybody in the system. So that's in a permissionless blockchain system. One winner is the leader, is able to add the additional block at the end of the blockchain, while the others just adhere to what was given to them and add it to their block, and then they start again the whole process. So the question is, does this blockchain data structure, this ledger that has blocks after the other connected with each other, which has several advantages? It gives us a provenance, it gives us the history of everything, it gives us a trace of how we evolved and how the current state was reached. Are there other applications other than cryptocurrencies? And turns out, surprise, surprise, there are lots of applications. In particular, there are many applications, and I'll just use this example, a supply chain in the real world, where it's used, for example, to keep track of fish and the production of fish, the fishing of the fish, the marketing of the fish, the delivery of the fish to the fish market, and eventually to the table where you're going to eat it. And what you're interested in is to know the trace of the food that you're eating through the entire system so that you can verify that it is fresh and is good. And blockchains have been used in this context. So you can use a seafood supply chain in a blockchain manner. When a fish is caught, you use RFIDs, you use sensors, IoT-enabled sensors to keep track of what's happening. Sensors continuously transmit location and time information, which is integrated into the blockchain to keep track of what's happening. So the blockchain system tracks possession, the changes that are happening throughout the system. So if, for example, eventually the food arrives at your table and it is not fresh, then you can identify whether the delay in the processing, in the delivery, happened at the fisherman's side or during the processing or during the transportation process. So there's a tracking of all the various times that have been happening throughout the history of this. So the buyer can access a comprehensive ledger or record of the fish's provenance. This is very interesting and useful in many various different contexts. So in general, we divide blockchains into two types of blockchains. What you have on the left is blockchains where anybody can participate without a specific physical identity and without knowing how many entities are involved in the system. This is typically what has been occurring in the context of cryptocurrencies. On your right-hand side, you have another system where the participants are known, are finite, are well identified from the very beginning, and they decide they want to work with each other. They might not trust each other, but they're going to work with each other. So we have permissionless or public or open blockchains, and we have permissioned blockchains. This tutorial is going to focus on permissioned blockchains. We are not going to be discussing permissionless blockchains anymore. We'll just focus on permissioned blockchains. So a permissioned blockchain consists of a set of known, identified nodes that might not necessarily trust each other. So this is the big thing that is happening when we bring these blockchains into the database world. In the database world, typically we assume that the storage devices are trustworthy, so they can crash, they might fail, but we don't assume maliciousness. However, in a blockchain world, you might have the fisherman and the transportation system do not necessarily trust each other. And it might be to their inherent interest to actually fool the system so as to get away with maybe delays that were unpredictable or whatever. So we have a set of known identified entities, nodes, that need to agree on this one data structure, which is the log, this blockchain. So you need to reach consensus among the various copies. This blockchain, this ledger, is being replicated on lots of different nodes. In a permissioned environment, they are well known, but they don't trust each other, so we need consensus among all of them. We need agreement among all of them, and typically what is used is practical Byzantine fault tolerance, and I will describe this briefly for you in a few minutes. This is in contrast, just to remind you, of permissionless blockchains, where the nodes are unknown and, of course, not trusted. In that case, we need to reach consensus, and the traditional terminology for that is that you do mining. In a mining system, you end up replacing the communication that takes place in a Byzantine agreement protocol with computation. You try to solve this puzzle, and the puzzle typically is a difficult puzzle, so difficult in the sense that it takes a long time to solve it. You have to explore an entire space to solve the puzzle, and so it's exponential in complexity. You don't have any shortcuts, and as a result, it takes a long time. Typically, in Bitcoin, for example, it takes about 10 minutes. One winner is the one who is going to be able to add the block to the blockchain. Now, let me just highlight some of the unique features and the reasons why people use blockchains. They are very useful because they provide provenance. For every asset, you know the entire history of it, you know where it has been and what has happened throughout its lifetime. It's immutable. Once a block is added, it cannot be ordered. We have a copy of it on all these various sites, and it cannot be ordered, so it is immutable. It provides us with persistence. It's fault tolerant because, as you saw, every copy of the ledger is stored on many different sites, so it continues to operate even if nodes fail or act maliciously. Since every party has access to the blockchain, it is transparent. Any party can audit all the contents of the blocks and determine whether everything is consistent or not. And finally, because the system is decentralized, the data is complete, consistent, is available in a timely manner, is accurate, and widely available. Before delving into more details, let's just ascertain what is actually a blockchain ledger. And this actually applies to more or less both permissioned or permissionless blockchains. So a blockchain ledger is an append-only structure. You have blocks and they are connected by pointers, and it's always appended at the very end. So at the very end. So you always are adding to the very end of it. Each block contains a batch of transactions, and the order of transaction execution is captured by chaining the blocks together. So this block is before, and the transactions in it are before the following one, and so on. Now the order is captured with these pointers, and to make sure that the contents are tamper-free and nobody, because we are storing these ledgers on untrusted infrastructure, we need to make sure that they will not tamper with it. So the trick that is done in blockchains is, in addition to a pointer, you actually include a hash of the previous block. This will guarantee that the blockchain is tamper-free. This is a cryptographic hash, which is very difficult to break. It's basically a SHA-256. The blockchain is stored in a large distributed system, basically a system on nodes that are in an asynchronous system. So here we have a bunch of nodes, and they are scattered potentially across the globe. The nodes maintain the state of the system, which is updated by executing transactions. Transactions basically read and write operations, data that is stored at these nodes. The blockchain ledger that we just saw on the last slide is replicated on all nodes. So it is fully replicated. Every node in the system has a copy of this blockchain, and hence can track everything that is happening in it. Nodes establish consensus to agree on a unique order. In particular, they need to add an additional block at the end of the blockchain, and we have to make sure that all of them have a consistent, unique order on all the blocks. So consensus is executed, and when a node becomes the leader, it needs to validate that all the new transactions in this block are consistent. Permissioned blockchains use traditional consensus protocols, unlike permissionless, which uses mining. So depending on the underlying assumption about the failure model for the nodes in the system, we might use, if it's crash, if we assume that they are crash, then we use Paxos. The more common assumption is that the nodes might be malicious and hence might act in a Byzantine way, and in that case we use PBFT. So what is the consensus problem? I've been talking about it. It's a set of nodes, distributed nodes, meaning they can only update data by communication, they need to agree with each other on a single value. In a blockchain, they need to agree on the next block that is going to be added to the blockchain. So before we get into the depths of permissioned blockchains and the various applications, I'm going to just give you a high-level description so that you are aware of the foundations of the protocols that are used in consensus in distributed systems. This will not take very long. The original proposal was for an asynchronous system, distributed system, and in the context of crash failures. So here I'm starting with a simple protocol for crash. So nodes are trustworthy. Paxos was proposed by Lamport, and what is typically used is a variation of it, which is used usually in distributed systems and especially in permission blockchain systems. It's called multi-Paxos. Paxos in general and multi-Paxos in particular have the notion that are leader-based. So there's one node that is going to be the leader of the system. In this case, it's node 0, and it has been elected. So there is an election phase that happens first. But in the steady state, you have a node that is assumed to be the leader. The clients typically know who the leader is. So in this case, we have one node, which is a client, and we have an object that is replicated, say, on 3 different sites, node 0, node 1, and node 2, and time goes from left to right, and we can tolerate some number of failures. In this case, I'm assuming that node 2 is the one that is going to fail. So a request comes, a client wants to, let's say, add a block to a blockchain. So what it does is it goes to the leader, whoever it thinks the leader is. If it's wrong, the message is forwarded to the leader. And the leader now, it knows it's the leader. It's going to make sure that this value is replicated on enough copies, on enough sites to make sure that it is fault tolerant. So what it does is 2 phases of communication, back and forth, or 1 round, where it sends out an accept message telling the different nodes in the system. In this case, it's going to call the 2 other nodes and itself. So it sends an accept message with the new value. Once it gets back an answer telling it that a majority, in this case 0 and 1, have the new value, have accepted this value, then you know that it is fault tolerant, it's going to be committed. So it commits it, and it replies to the client saying, yes, your value has been committed, and informs everybody else that the value now is committed. Notice that at the end of the accepted phase, only the leader knows that the value has been accepted. The other nodes, in particular node 1, does not know yet. It just has answered back, but it doesn't know if a majority have already accepted it or not. So the leader has both the responsibility of committing the value, replying to the client, and updating the other nodes in the system to inform them of the new value that has been committed. So this is basically multi-Paxos. To tolerate F crash failures, you typically need to have quorums, and the quorum is typically a majority. In general, it is F+1, and any 2 quorums must have an intersection of at least 1. So if you want to tolerate F failures, you typically have a network of 2 F+1. To do anything, you need to get agreement or a quorum from a majority, F+1, and you'll notice that the intersection between any 2 quorums is 1. The protocol has 2 phases. Once the leader is elected, all it has to do is it has to send accept and wait back for accepted messages. So the complexity is big O of n. It's linear in the number of nodes that are in the system. So this is basically a high-level description of Paxos. Paxos tolerates crash failures. However, as I indicated earlier, we are interested here in tolerating malicious failures, in tolerating nodes that are not trustworthy, nodes where the response to a message might deviate from what the protocol is describing. So the foundational protocol for that is what's known as practical Byzantine fault tolerance. It was developed by Castro and Liskov in 1999, as you notice, almost just briefly after Lamport's Paxos protocol. It is also for asynchronous systems. It is also based on a notion of a leader who dominates and facilitates the updating of values. However, it is designed for malicious failures. To tolerate malicious failures, and I'll tell you now, you need to have at least, you can tolerate at most 1/3. So F is at most 1/3 of the number of processes. So here I have an example. Again, these timelines go from left to right. We have a client with a new value, and to tolerate one failure, in this case node 3, who might not only crash, but might actually lie. So it might, in the previous example, always the crashed site never sent any messages. However, now the failed site might send messages, but they might be incorrect. So we have at most one failed site, and we'll have 3 other processes. So with 4 processes, you can tolerate 1 failure. Again, the client sends a request with a new value, let's say the block in the blockchain, to the leader. What the leader does is it sends what's called a pre-prepare phase, where it sends this new value to all processes in the system. So it sends it to the other sites, as you see. What can happen now is that the node 0 might be malicious. Node processes in the system are not aware of this. So as a result, there has to be agreement on the value that it's sent. As a result, we cannot continue as we did with Paxos immediately to a commitment. Instead, the different sites in the system exchange with each other the values that they received. So the prepare phase is when each site sends to everybody else. So n² messages here are being sent to everybody else. These are sent to each other to validate what value they received. Once every site has received the prepare phase, they can again exchange messages with each other, so n² again, to commit the value. If at the very end of the commit phase, a node receives consistently all values that are, well, a quorum of values that are consistent with each other, then the value is committed. So you need to get here from a quorum, and the quorum has to be consistent in the value that it's sending to each other. If nodes receive this, then what they do is they respond back to the client with the value and the reply with the value that they committed, and the client needs to get at least f+1 consistent messages with each other to tolerate the potential of F failure. So if you get f+1, you know that they have the same value, that they are adding the same block, let's say, then it must be consistent with each other, because you can't have more than F malicious failures. So in this case, we have quorums, and the quorums are 2F. So to tolerate F, I need to have quorums of size 2F+1 and the network of size 3F+1. Or put it in other ways, if I have n processes, 1/3 of them need to be, I can tolerate at most 1/3 of them failing, and I need quorums that are 2/3 of size. Why do I need 2/3 size quorums? Because as a result, if the intersection of 2 different quorums Each of them of size 2f plus 1 will result in an intersection of f plus 1, and if all f plus 1 values are identical, the returned values are identical, then we know that the value is consistent, because is correct, because out of those f plus 1 there can be at most f failures, so there's one of them that is correct, that is not lying, and since they all agree on the same value, then we know that that value is the value, and that's the correct value. What you'll notice is that unlike with Paxos, we now have 3 phases of communication, and there's an explosion in the number of messages. Instead of a linear number of messages in the number of sites that we have in the system, here we have order n square. And of course, the quorums have increased in size. So Paxos is a foundational protocol that is used to reach agreement and consensus in distributed systems. It's the foundation also for practical Byzantine fault tolerance, and PBFT is the foundational protocol that is used in most blockchain systems, permissioned blockchain systems that need consensus. Typically, they assume that you don't trust each other, so they use PBFT. Sometimes we develop a permissioned blockchain system in a system where the nodes actually trust each other, and in that case we can actually have the easier case where we can use Paxos, and as you saw, it has several advantages, both in terms of latency and in terms of throughput and communication. Latency, notice, is a direct function of the number of phases that you are executing the protocol. Paxos needs 2 phases, while here we need 3 phases of communication. Okay, so this was just so that we are not going to delve more into details about these protocols. We are going to use them, but I wanted to make sure that you are comfortable with and are aware of the foundations of these consensus protocols. So now we want to use permissioned blockchains in various applications to help us to facilitate various applications. So for example, if I would like to use blockchains in a financial environment. Why would I like to do this? Because it gives me the provenance of all the various transactions that are happening in the system. So it's a very powerful, it gives me a trace of everything that has happened in the system. However, the challenge with financial systems is performance. Typically with Visa, with credit cards, with banking, you have tens, if not hundreds of thousands of transactions being processed in 1 second. Blockchain systems are much slower. Their performance, their throughput is much less than this. For example, if I was in a permission-less environment, our performance is actually, as I mentioned, it takes about 10 minutes to solve the puzzle. So as a result, you have 7 to 10 transactions per second being executed, while in the real world, we need a lot more performance, even a lot better performance. Even if we change to permissioned environments, as you saw, the permissioned blockchains require consensus, and if you are assuming Byzantine fault, if we're going to use PBFT, it requires 3 rounds of communication. As a result, the performance is actually not as good as the strong database systems that you have all been developing and working on. We've been working really hard in the last 30 or 40 years to radically improve the performance, the throughput of transactions in commercial database systems. Using permissioned blockchain systems is not competing enough. So we're going to explore ways in which this can be achieved. Another environment that I've mentioned earlier is the supply chain environment, where you have various entities that do not trust each other and who want to work with each other. Maybe the performance isn't a big issue for them. However, in this case, we have a problem of confidentiality. In a blockchain system, as you saw, the blockchain is a series of blocks that refer to everything that has been happening in the system. The whole notion of a blockchain is to be able to see the provenance of all the transactions that are occurring. As a result, there is a lack of privacy. There's a lack of confidentiality. And this is a challenge in an environment where we want to support different entities that might want to hide some information from each other while sharing other information. Why not use blockchains in large-scale database systems? As I've alluded, we would like to do this, and in large-scale systems, we have very good performance. The challenge here is that it doesn't scale. The way blockchain systems, permission blockchain systems, did not support scalability, and we need to inject ways in which we can support scalability. Finally, a new application that has arisen is to use blockchains in crowdsourcing environment where we have a provider like Uber and then drivers, and they need to work with each other. In such environments, we need to verify that everything that every entity is doing is actually adheres to the rules and regulations of the system, whether it's labor laws or healthcare regulations, etc. So I would like to inject into my blockchain tools that will allow verifiability. What we are going to do in the rest of this tutorial is to explore these different aspects. So we are going to look at performance, and we're going to explore various different ways in which performance can be improved using different techniques that are optimistic, pessimistic, using notions that are very familiar to database people to improve the performance. We will explore confidentiality issues, whether we can split the blockchain into different components that are view-based and seen by different entities but not by others, or to use cryptographic techniques. We're going to explore scalability. So as I described it, we have a ledger in a blockchain system. Maybe we might want to shard this blockchain ledger. So as a result, improve performance. And finally, verifiability, how to ensure how to be able to verify certain aspects. For example, we could use zero-knowledge proofs or tokens. So overall, what we're going to try and do is to show you how various techniques that some of you might be familiar with from a database world, to apply them in an environment with permissioned blockchains. I'm going to stop here, we'll take a break, and then we'll continue around this cycle. See you later. Bye.